Hello students. Today I shall talk about simple harmonic motion, damped harmonic motion, and also the forced harmonic motions. First of all, I should explain the simple harmonic motion, then I should explain the damped harmonic motions and what can be the equations of damped harmonic motions, and forced harmonic motions. So what can be the equation that is suited for forced harmonic vibrations? Now, as the very name suggests, the simple harmonic motion, it means it's a very simple motion, as the very name suggests, and the motion must be in a harmonic manner, and of course the motion should be there. Motion means it must be in a moving position, it must not in a static position. So the word simple, it comes before harmonic. Now the word harmonic actually means that the motion has got a periodic manner in the sense that a particular position within its the way in which it is moving, the path in which it is moving. So the particular object which is moving, it is crossing a particular point after a certain period of time, after a certain fixed period of time, and then this motion is called periodic motion. So it is maintaining a period basically. After a certain amount of time, after a certain time, it is again coming to that point. So that's why this is called periodic motions. Periodic motions, it is going in this way, it is coming again in this way, again it is going back in this way. So if you consider a particular point, so you can see that a particular point is crossing, a particular point is being crossed by this object after a certain particular amount of time. So this is a harmonic motion. This is called harmonic motion. Now a simple harmonic motion. Simple harmonic motion, what does it mean? The simple harmonic motion, it means there must be a relation of this motion with the displacement, because the acceleration, in case of simple harmonic motion, the acceleration is proportional to displacement. This is simple. Acceleration is proportional to displacement. The motion must be harmonic. If the harmonic motion is bounded by the equations, with the equation in which the acceleration is proportional to displacement, then this is a simple harmonic motion. So you can see here, acceleration, mass into acceleration is the force. Mass into acceleration is the force. So accelerations in the calculus notations, we can say like this, that this is d2x dt square. If x is the displacement, then d2x dt square is the acceleration. Now m into d2x dt square is nothing but the force, mass into acceleration. According to Newton's second law, it is force. Now m into dtx dt square, that is proportional to displacement x with a negative sign, minus, because when it is accelerated, means the acceleration is a direction in which it is increasing, the displacement is decreasing. Suppose it is here. Now the acceleration, if you go in these directions, it is going upwards. It means if it is going upwards, then you see that displacement, actually displacement is taking from the mean position. Mean position means this is, suppose, from these the displacement is taking. Now displacement when increasing, the acceleration is decreasing. Now when it is coming downwards, so very well you can see that, very well you can tell also that when it is going downwards here in these positions, the acceleration should be highest, and when it is going upward, the acceleration should be lowest here, and then again it will come, the acceleration will be highest here. So acceleration should be highest at the position x is equal to 0, because x is measured from this position. Now it is going upward, x is increasing, acceleration is decreasing. So since the acceleration, increment of acceleration is associated with the decrement of the displacement, so here a negative sign appears. Now m into dt x dt square is equal to minus sx. S is one is constant, stiffness constant. So m d2 x dt square is equal to. Now what will be for forced harmonic vibrations? Now if this is like this, if this is like this, now it may be a damped motion. In practical it is damped motion, suppose. Now it will stop after a certain time. Now if you just struck here, it is when it is coming in this position, you start, coming in this position, start, coming in this position, start, coming in this position, start. So the motion will not stop. It will go on because you are striking. So if you are striking, the motion will go on. So you are giving a force. You are giving a force here. So the forced harmonic vibrations now comes into play. The forced harmonic vibration, if you see that you are applying the force in a direction, you are applying the force in a direction, the motion is going in these directions, you are applying force here. If you apply force here in the same directions, then this will not work. Suppose it is going there and you are applying your force here. But if it is here, you are applying here, you are applying here, it means both the directions are opposite. So the equations here, that is that m into d2x dt square minus sx minus k into dx dt, and just negative to that, just opposite to that, the force F sine pt. P here is the frequency, the angular frequency actually, for the force which are applying. That is also a periodic force. If it is not periodic, periodic means it is coming here and you are striking. You are coming here, is striking. Coming here, is striking. Suppose you are here and you are striking, it is going there. There is no question of forced harmonic vibration. Now when it is coming here, you are striking. When it is coming here, you are striking. Maybe that the frequency of the striking is maybe different from that of the frequency of this motion. Here you see that the frequency of this motion and this frequency of the striking. Suppose the frequency of this motion is omega, and the frequency of the striking is p. Here it is p. Then the m into d2 dt square is equal to minus sx minus k dx, and this is in the opposite directions of this. So plus, here the plus will come, plus f sine p. This is the equation for the forced harmonic vibrations. Again, here the natural frequency of this motion is omega. Natural s by m is equal to omega square x. Suppose s by m is equal to omega square, you can say d2x dt square is equal to minus s by m into x. S by m is omega square. Now omega is the frequency. So omega is different from that of p. So what will happen? So after a certain time, this omega will die out, and the whole motions will be in a frequency p. Will be in a frequency p. You are striking with a frequency p. The motion is also having, after a certain moment, will also have some frequency p, and in this p frequency, it will then fluctuate. Sure. So actually we see that there is a natural frequency omega. After a certain moment, it will be damped, and after a certain moment, it will have a frequency which is equal to p. So now there must be a transition period from which it is coming from the frequency omega, the natural frequency, to the frequency p. And that in that transition moment, there must be one point where omega is equal to p, and then the resonance occurs. So the resonance word you cannot find in the damped motion. The resonance only comes in the forced harmonic vibrations. When you read the book, when you will go through the books, you will see that the resonance point is coming in the forced harmonic vibration. Why? There are two frequencies. One is omega, one is p. And at the point of transitions, there must be some point when omega is equal to p and the resonance appears. Omega is equal to p, then the resonance appears. So it is coming. And when the resonance appears, the amplitude become higher, all of a sudden. So it is going like this, it is going like, all of a sudden the amplitude will be higher. Amplitude will go jump when the resonance. Then again, it is having a frequency with the frequency than that of this forced harmonic, that is the force applied. So the force is applying is a periodic force. And of course, with that periodic force, the frequency that is being applied by that force, it will gain this frequency, and after that, a forced harmonic vibrations will appear. If you go for the equations, simple mathematics calculations, then also you can see, if you solve it, so you will have two parts. One is the damped part for this, and the other is for the part, for harmonic part, forced harmonic vibration part. So there will be two equations. There will be, if you have a mathematical solutions, then also you can find this, and physically also you can find it. So this is about forced harmonic vibrations. So I think all the students who have understood the simple harmonic motion, the damped harmonic motion, and the forced harmonic motion at a glance, and physically, then you just taking into these all things in your mind, you just go to the books, then you can enjoy the whole books of this acoustics, simple harmonic motion, damped harmonic motions, and the forced harmonic motion. Thank you. So, m d2 x d2 square is equal to minus sx. This is an equation for a simple harmonic motion. Now, whenever there is any motion, any simple harmonic motion, so there is always a hindrance, there is always an obstacle. See, maybe comes from the particle collisions of the air. Suppose it is going in this direction, some air particles are there, and it is going through the air. So the particles of the air has got some obstacle, and that's why after certain time, it will go like this, and after certain time it will stop. Why it will stop? Because of the fact that the motion becomes damped, it becomes damped. So damped harmonic motions, and you can see that the motion which is damped, if the velocity is higher, then there will be more obstacle from the air particle, more collisions will be there. So if the velocity is lower, it is going very, very slow, then the less collisions from the air particles. Suppose I am taking into consideration the air particles only. There are other kinds of obstacle may be there. So you can see the motion is basically proportional to the velocity. If the velocity is higher, then it will be more damped. If the velocity is lower, then it will be less damped. So the velocity factor dx dt comes here. So it is proportional to the velocity. So the main damped factor is k into dx dt. And k into dx dt is again the negative sign should be there. Because here again, when the velocity is higher, the collisions will be higher, and the motion will be more and more damped. So the displacement will be lesser. So again, you can see that m d2 x dt square is equal to minus of sx minus of k into dx dt. This is the equations for damped harmonic vibration.